Okay, this will serve as the complete solutions for Chapter 12, Section 4 practice problems for doing derivatives of exponential functions, functions where there is an exponent on a base. And pay careful attention to the role of the numbers in the problem that I'm going to first do, because we have to make sure we understand exactly what the function is. So in this first one, that 3 is actually a coefficient or a multiplier. And because it's a coefficient or a multiplier, it's just going to kind of hitchhike along with the rest of the function when we do the derivative. So the actual derivative part for the exponential part is e to the 5x. And the derivative of any power of e is f prime of x would be also e to that same power. So this would be e to the 5x. But because we have that 3 in front, that 3 is going to come right along with it. And then this is now a chain rule problem, and we'll have to take the derivative of 5x and multiply it times the rest of this. So we have 3e to the 5x times the derivative of 5x is 5. And so f prime of x is equal to 3 times 5 is 15 e to the 5x. In our second problem, we have 2 as a multiplier, so our derivative is going to carry along that 2. And then our exponential expression is e to the 4x plus 1. So the derivative of that is e to the 4x plus 1 times the derivative of 4x plus 1, which is 4, or 4 plus 0, since the derivative of 1 is 0. And that means then that y prime will be 4 times 2 is 8 e to the 4x plus 1. Here we have y equals 5 times e to the 3x squared. So just as before, y prime, 5 is going to hop on over to the derivative and just sit there and multiply like it was doing to start with. And the derivative of e to the 3x squared is e to the 3x squared, but the derivative of 3x squared, again using chain rule, would be 6x. So y prime equals 5 times 6 is 30 times x e to the 3x squared. And in problem number 4, we actually do have something different, because this, in fact, now is a product rule problem. It is the product of the first function times the exponential function. So we have to take the derivatives of both of those functions. And so the product rule says to take the derivative of each one. So we're going to do that. The derivative of 6x squared is 12x. And the derivative of negative 12x is negative 12. And the derivative of 12 is 0, so we'll leave that alone. So this is the derivative of factor number 1. The derivative of factor number 2 will be e to the negative 3x times the derivative of the exponent, which is negative 3. And so that derivative is negative 3 e to the negative 3x. And then the product rule says that we will take the first expression 6x squared minus 12x plus 12, and multiply it by the derivative of the second factor. So that's going to be multiplied times negative 3e to the negative 3x. Then we're going to add, because that's how we take the derivative. It's the sum of the first factor times the derivative of the second factor plus the second factor, which is e to the 3x. I'm sorry, negative 3x. And then that's going to be multiplied times the derivative of the first factor, which is 12x minus 12. At this point, the calculus is complete. Now, my math lab does a lot of different things, and sometimes I really wonder why they do some of the things that they do. But I'll try as best I can when I know what they're liable to do to explain to you what they are going to do. One thing they're certainly going to do here is they're going to notice that there's a common factor between those two terms in the numerator of e to the negative 3x. So they're most likely going to factor out e to the negative 3x. And so what we'll have left is we're still going to have this negative 3, and we're going to have to distribute it to all three of those terms. So negative 3 times 6x squared is negative 18x squared. Negative 3 times negative 12 is plus 36x. And negative 3 times 12 is minus 36. And then we also have plus 12x minus 12. So when we combine all of this, we have y prime is equal to e to the negative 3x times negative 18x squared. 36 plus 12 is 48x. And negative 36 plus negative 12 is negative 48. And this is more likely the answer that my math lab is going to say is the correct answer. However, this very first answer is actually correct. It just isn't in a very compact format. If this were a 5-point problem, going the extra mile to do this part of it would probably be 1 point. And the first step would be the other 4. The only time you have to simplify completely is if I tell you to. But on the ones that I see that my math lab is likely to do that, since I know some of you are doing the my math lab homework, then I do try to show you what they might do in the name of simplifying. So here we have a quotient rule problem. The numerator is negative 4e to the 3x, and the derivative of that numerator is negative 4 times e to the 3x times 3, which is the derivative of the 3x. So the derivative of your numerator is negative 12e to the 3x. The derivative of your denominator, since your denominator is just 7x plus 2, its derivative is just 7 plus 0, or 7. And then the quotient rule tells us to start off with the denominator and square it, then lead off in the numerator with the denominator of the original function times the derivative of the numerator minus the numerator of the function times the derivative of the denominator. So when we put that into action, then y prime is going to be the denominator, 7x plus 2. And it's also going to be in the denominator, 7x plus 2. But it's going to be squared in the denominator. And in the numerator, it will be multiplied times negative 12e to the 3x. And then from that, we will subtract the numerator, which is negative 4e to the 3x, and we multiply by the derivative of the denominator, which is positive 7. And at this point, you have, once again, done the calculus, and the rest is algebraic simplification. And the trick that we used before is going to remain the same. There's a common factor here of e to the 3x. And so we'll factor out that common factor. And when we do, we have negative 12 times 7 is negative 84x. Negative 12 times 2 is negative 24. And positive comes from the negative times the negative, so this will be positive. 4 times 7 is 28. And again, the e to the x is out front. And of course, that's all still divided by 7x plus 2 squared. And then once you've made that simplification, you have two constants here together, so you may as well add those two together. And still keep your denominator exactly the way that it is. That's as simple as we need to have that. And so there's your My Math Lab version of the answer. That's completely simplified. Now, question number 6 can be done as a quotient rule, but it can also be done as a product rule. I don't necessarily recommend doing it as a product rule by moving the x up to the numerator and making it a multiplication problem, because the quotient rule in all reality is probably easier. So the derivative of your numerator is going to be e to the 5x times the derivative of 5x is 5 e to the 5x plus e to the negative 5x times negative 5 So we're going to actually be saying plus negative 5 for the derivative of the 5x, the negative 5x. And then that's times e to the negative 5x. And it would be simpler to write this as 5e to the 5x minus 5e to the negative 5x. And fortunately for us, the derivative of the denominator, which is just x, is just 1. So when we get ready to write y prime, we keep the denominator, which is x, and square it. We take the denominator to the numerator and multiply it by the existing numerator, or actually by its derivative. And the derivative of that numerator is 5e to the 5x minus 5e to the negative 5x. And then because it's a quotient rule problem, then we're going to subtract that numerator, which is, again, e to the 5x plus e to the negative 5x and that's times the derivative of the denominator, but that derivative is just 1. And so our y prime actually simplifies we have e to the 5x multiplied by x and then negative 5e to the negative 5x multiplied also by x. And then that's minus e to the 5x plus e to the negative 5x. And I have run myself out of room. So let's try rewriting that. And since the parentheses are in front, this factor should be negative e to the negative 5x. And this is all over x squared. That doesn't look a whole lot simpler, but it is as simplified as you can make it. There could be some fancy factoring they might do. They might try factoring by grouping, but personally, I don't really see the need to do that. And unless you just want to, we would leave it just exactly at this and not go any further. So we'll move on to the one below it and pay careful attention here. While this appears to be a quotient rule problem, it actually is and it isn't. I'm going to do it as a quotient rule problem. You could do this one as a product rule problem, but you'd have to deal with a lot more exponents. So we're going to do again a quotient rule problem, but something nice is going to happen. When we take the derivative of the numerator, that derivative is going to be 0. And when we take the derivative of the denominator, that's going to be 0 plus -6, which is the derivative of this power, times 6e to the -6x. And so our derivative of the denominator is -6 times 6 is -36, e to the -6x. And now we'll do our quotient rule. So y prime says start in the denominator, and the denominator is 31 plus 6e to the -6x, quantity squared, and then take that denominator to the numerator, 31 plus 6e to the -6x, times 0, which is the derivative of the constant that's in the numerator, plus the numerator, which is 575, times the derivative of the denominator, which is -36e to the -6x. And so ultimately y prime, because this is 0, that all cancels out. And if you multiply 575 times -3, I believe, oh, and I have a sign problem here. Let me fix that before we go on. This should be a subtraction, not an addition. So if you multiply -575 times -36, I believe what you get is 20,000. Better check my arithmetic here. $20,700. And that's times e to the -6x, all divided by 31 plus 6e to the -6x, quantity squared. And there is absolutely nothing else to do to that, but just keep that the way it is. So here we've got a chain rule problem with a pair of terms inside the parentheses. And if you remember your chain rule, we would start out by bringing the 5 down in front, multiply it times 8z plus e to the -z squared, and reduce that power by 1, making it 4. And then we would need to take the derivative of what's inside the parentheses. And the derivative of what's inside the parentheses, the derivative of 8z is 8. And the derivative of e to the -z squared is e to the -z squared multiplied by -2z, which is the derivative of that power. Now, you could multiply this out, but there's no real reason to. I would leave it exactly that way. So this is f prime of x. And then here we have another exponential expression, but this is not a base e. Now, when the base is e, we're actually doing the same thing we're about to do here. This is a function where you have a number, which I'm going to call that number a constant, and it's raised to a power. And when you try to find f prime for that, what you have to do is you have to do your regular chain rule problem, but you have to include a factor of the natural logarithm of whatever that constant is. And so that's what we're going to do first here. Y prime is going to be, first of all, the natural log of -6, but we got a problem there, because if you try to do the natural logarithm of -6, guess what? It tells you that that's not real. So we're going to get around that. The way that we're going to get around that is we're going to treat the negative as if it's the coefficient -1 times 6 for all that. So that -1 now becomes just a hitchhiker. And we can take the natural log of +6. And then we need to take the derivative of 6 raised to the power 8x squared minus 5. And then the derivative of 8x squared minus 5 is 16x plus 0. So we'll just leave that off. And so ultimately y prime is -1 times 16x, which is -16x, times the natural log of 6, multiplied times the exponential expression 6 raised to the power 8x squared minus 5. And there again, there's no need to go any further than that. Just realize that this itself is a number. It's just that it's a decimal number. And it is correct that this is the natural log. It is not the base 10 log. It is the natural log. Power So here we have problem number 7, and problem number 7 is a little challenging, even though it doesn't look like it on first glance, because there's two different ways to do it, and depending on which way you choose, your solution will be equivalent if you do it correctly, but they won't look anything like one another. So method 1 is to treat this like a product. Which means that you're going to take the derivative of 7. We're going to split it like that. And so the derivative of 7 is 0. And the derivative of 7 to the x squared minus 9 is the natural log of 7 times 7 raised to the square root of x minus 9 times the derivative of the square root of x minus 9, which is x minus 9 raised to the negative 1/2 power. And that's because this is actually 7 times x minus 9 raised to the 1/2 power. And so when you get the derivative, that drops the power down to negative 1/2. And it also puts a 1/2 in front. Or behind, but it includes that factor. Oops, wrote that wrong. So this one has kind of a long derivative. So then if you do it by multiplication rule, the product rule, then it's first, which is 7, times the derivative of the second, which is 1/2, bring that out front, times the natural log of 7 from there, times 7 to the square root of x plus 9, times the rest of the derivative of this, which is 1/2. Whoops, already used the 1/2, sorry. We already used the 1/2 out front, so all we have left is this part. Plus the second factor, but when you multiply it by the derivative of the first factor, that part disappears. And it leaves you with this. And you can clean that up to look a little bit better. 7 times 1/2 is 3.5, or 7/2 if you want to keep the fraction. Times the natural log of 7 times 7 raised to that same power. And since this power is negative, we bring it down to the denominator, and it becomes a positive 1/2 power. And you can take all of that back into the radicals. And so that's what your derivative looks like using that rule. Now the other rule that you could use would come from doing some algebraic simplification first. And that would be y is equal to 7 to the first power times 7 to the square root of x minus 9 power. And you should remember from your exponent rules that if you have the same base and different exponents, you keep the base and you add the exponents. And so that means this is y. And if that's the case, then y prime is once again the natural log of 7 times 7 to that power times the derivative, and the derivative of 1 is 0, and the derivative of the square root of x minus 9 is 1/2 for the square root times x minus 9 to the 1/2 minus 1 is negative 1/2 power. And so that means that we have 1/2 times the natural log of 7 times 7 to the 1 plus the square root of x minus 9 power times x minus 9 to the negative 1/2 power, or you can do what we did up here and move that to the denominator. Now I know it looks like we lost something, but we didn't. Even though it looks like we did, we didn't. Because this 7 to the first power actually could still be brought back out here if you multiply all this out and broke it back down. It would multiply back out and come back to this. But they do look very, very different depending on which approach you take. So be sure and show me the entire process that you used so that I'll know what approach you took. So this one I simplified the function before I tried to take its derivative. This is probably the most challenging problem on that set of exercises. Problem number 11 is an application problem. When you have an application problem and you are given a specific value for the variable, which we are here, then it is perfectly okay, unless I ask to see the formula for s prime of t in this case, it's perfectly okay to use n deriv, because I'm only asking you here to find the rate of change of sales. And this is your sales. And so what we would do is we would go to the calculator and use Math 8 to get n deriv. And on the 83, the first thing we do is enter the function s of t. And since the calculator doesn't have a t, we'll have to replace t with an x. And then that's going to be with respect to x at the value x equals 8. The 8 coming from here in the problem. If you have the 84 calculator, it doesn't look exactly like this. On the 84, when you do n deriv, you get d over d and a box to fill in. And that box has to have x in it. Then you put in your function. And then close the parentheses. And after that, there's a line, and there's an x at the bottom of that line that says equal to, and you have another box to fill in. And that's where your 8 would go. And if you do either process, you should get the correct numerical answer. which is 0.1294. And it says round to the nearest tenth, which would be 0.1. And then you have to answer the question. So, after 8 years, sales are increasing by 0.1 thousand per year. And sales in thousands doesn't necessarily mean that's in thousands of dollars. That could be that that's meant that many thousand products increase in sales. So 0.1 thousand, alternatively, you could say, is 100, because 1/10 of 1,000 is 100. So sales are increasing by 100 sales per year. The focus here is on the explanation, not on the calculation. You do need to get that right, but the calculator will give it to you correctly. Now, in this case, I actually ask you to find the marginal demand. That means I want the formula. And if I want a formula, I also want the units. I don't want the word marginal to come out in the answer. I want the units for it. So our marginal sales is going to be D prime of T. I'm sorry, D prime of P. And P would, of course, be the price, the demand at a certain price. So 68 is the hitchhiker. Keep your e to the power. But then take the derivative of that power. And multiply by it so that you're using your chain rule. And 68 times negative 0.004 is negative 0.272. E to the negative 0.004 P. And so this is the demand is changing by because it means it could go up or down. Just because that negative is in front doesn't necessarily always mean that that this would have to be negative. Depends on what the price is. The demand is changing by negative 0.272. E to the negative 0.004. P per dollar increase or you could say per unit of increase, since we don't know for sure if it's in exactly dollars or if it's in hundreds of dollars. So per unit of increase in the price. Now, in all likelihood, this change is going to be negative. So that actually means that your demand would be decreasing. As the price goes up, which should make sense because demand generally does decrease when the price increases, because people don't want to pay more for something. But here again, be sure that you got your units and that you're using that word per because it's a rate of change. Marginal means rate of change. This problem looks challenging, but it doesn't have to be. There's actually two different formulas you can use for this. The one that I'm giving you here is actually the more complicated of the two, but it tells you better where things are coming from. So we're going to see if we can pick out all this information. So we're going to try to find G of T, which is the growth function for the number of internet users in this country that we're looking at. So G of T is going to be equal to this formula with some numbers plugged in. It says T represents the time in appropriate units. In this case, T is probably going to be in years, since we're looking at the years from 1990 to 2015. And in fact, it says that T is the number of years since 1990. And so when we read what everything stands for, G sub 0 is the initial number present. Okay, initially we're looking at the year 1990, which is when T equals 0. And at that time, the number of users was about 2 million. So that means G sub 0 equals 2 million. And we're just going to call it million. We're not going to write out 2 with all the zeros. So that means that 2 is going to show up in our formula here, here, and here. And then it says that M is the maximum possible size of the population. And it says the number is expected to level out at around 240 million. So that means M is then equal to 240 million. And it shows up here and here, and also in the exponent. And so the parentheses are actually part of the problem. And so is the base E minus K to the N, K times M times T. And it says here K is a positive constant unique to the problem. So for right now, we have to go back up here and find out what that unique constant is. And it's approximated by a logistic function with K equal to 0.0017. And notice the negative sign actually is part of the problem also. So then we're going to multiply that times M, which was 240. And that's all times T. And T is the number of years since 1990. So when we make our explanation, we need to make sure that that's obvious. So I'll slide this up a little bit, and the other form will give you the same answer I'm about to simplify and get. So G of T is equal to 240 times 2 is 480. Divided by 2 plus 240 minus 2 is 238. Times E to the negative 0.0017 times 240, and I'm going to come back and multiply that out too, times T. So that comes out to be negative 0.408. And then to completely achieve the other formula, what I'm going to do is I'm going to look at the fact that this term has an even coefficient, and this term has an even coefficient, and this number also has an even coefficient. And so I'm going to factor out that coefficient, which is 2. So 480 is 2 times 240, and 2 times 1 is 2, and 2 times 119 is 238. And at this point, we can cancel out those 2's and arrive with the most compact version of G of T that you can get. G of T is equal to 240 over 1 plus 238 e to the negative 408 after the decimal t million users in that country t years after 1990. And so that's the function that we're going to need. And what I would have you do at this point is I want you to go into your calculator and I want you to go to your y equals menu and I want you to enter the growth function g of t. So that's 240 divided by, be sure you put parentheses around the denominator, and I want you to enter that formula. And probably if it's on the 83, probably it's going to open up a set of parentheses here. And I believe I left out my e, so I better put that in there. Because these parentheses would have been here. So on the TI-83, there may be a power symbol there, and then there'll be parentheses that you'll need. But on the 84, it probably just makes the power when you press the power key. So it may look a little different, but enter that function into your calculator. Be sure this is a negative sign, not a subtraction sign. And then on Y2, I want you to go to end deriv. And the value of the function is going to be y1 with respect to x for all values of x. Or it's going to be d over dx y1 at x equals, and put the x there. So be sure you've entered this into your calculator. Because we're going to use the calculator to get the numerical derivative of that rather challenging little formula. So you can hit pause, enter that in your calculator, and then you can start the recording up again. So then what we're going to do, once we've got that in the calculator, we're going to go to the table. And we want to first go to second window and set the table where it says independent. To ask. And the dependent will be on auto. And so this is what's going to happen. We're going to come up with a table where X is number of years after 1990. The second column, Y1, is the value of G in that year. And then Y2 is going to be the rate of change. Or the marginal growth. And for our first table, this problem says we're going to put 1995. So what we're going to do is we're going to enter the value there of 5. Now I'm going to page forward for a second and get the other numbers. In 2000, T is equal to 10. 1990 plus 10 is 2000. So 10 years have passed. In 2011, 21 years have passed. And then it's also going to ask us to look at the rate of growth over time. So we're also going to look at what happens at 25 and 50 and see if we can determine what's going on after that. So pause it at this point. Make sure you've got the function in. I'm going to have to go back and enter. So in 1995, there were 723 million. $7.723 million internet users. And that was increasing by 5 million per year. And in 2000, something's not working. So we're going to read the rest of this problem now. And what we want to do is we want to estimate the number of internet users in the country and the rate of growth for the year 1995. And remember to include the units, which we will, because it's millions of people that are internet users in that country. So for our first year, that's 1995, and I'm going to jump ahead a little bit. in 2000 and 2011. And then we're also going to make that same estimate for the year 2000 and for the year 2001. And we're going to answer the question then, what happens to the rate of growth over time? So at the bottom of this page, what I'm going to do is I'm going to build a table to help us answer that question. So remember, what we have in Y1 is g of, we're going to have to call it x, even though it's actually t. And the first column in that table is going to be x, which is the number of years since 1990. So in 1995, and I don't think I'm even going to put that in the table. I think we're just going to keep that to what you can put in your calculator. In 1995, the value of x was 5. And then in the year 2000, it was 10. And then in 2011, it was 21. And then since we want to look at the rate of growth over time, then we'll go to 30 and 40 and 50 and see what happens. So Y1, remember, is your number of internet users in the country, in millions. Y2 is your growth rate. How fast is your population growing in that year? And so if you set the calculator up the way that I told you to, all we'll need to do is enter in 5, and the answer that we come up with is 14.568. And our rate of growth is 5.583 million users per year. So the population is increasing by that much. So in 10 years after 1990, which is the year 2000, the population has grown to 79.681 million people that have internet, and the population is still increasing by 21.717 million people per year. In 2011, the population has reached 234.691 million internet users in that country. And the rate of growth now is down to only about 2.118 million people per year. So our growth rate is actually leveling out. We see the growth rate is shrinking. And then when we try to answer the last question about what happens to the rate of growth over time, then we can plug in some of these other numbers and see what happens. So 30 years after 1990, that'll be in the year 2020, the population of internet users in that country is 239.862 million people that year, but the rate of growth is down to 0.056 million people per year. So less than 500,000 people, in fact, less than 0.1 million people per year. And so if we also go ahead and look at 2020, then we should look at 2030, which is 40 years after 1990. Population's still pretty close to the same, 239.998 million. But your rate of growth now is practically zero. It comes out in scientific notation, so it means that your decimal has to be moved 4 places to the left. So it's growing by 1/10,000th of a million people per year. And then 2040, which is 50 years after 1990, the population is still sitting right at 239, almost 240,000. So the population hasn't grown very much, and in fact, the rate of growth at the end of the 50th year after 1990, there's only 1/1,000,000th, less than 2 millionths. So the growth rate actually has slowed down and stagnated. So the population levels out over time, and that's probably because after a while there's no more people that are living there that don't have access to the internet. So unless the population grows significantly for some reason, there's not many more people to actually add to that population. And so that concludes our lesson for section 12.4, and I hope this helps, and I will work on section 12.5.